So now we've basically now so far understood what backpropagation is, okay? And backpropagation is the key in all of this. In fact, that was one of the key contributions which made neural networks very popular, right? And this happened, even most of these algorithms actually are not new. Even the backpropagation algorithm was quite old. But simply because of, again, big data, and because now you had enough processing power and you had GPUs, because if you look at all of these equations, they can be done a lot in parallel, all right? If you need to update all of these equations for each one of these values of the weights, they can all be done in parallel. And if you have graphical processing units, which are highly parallel, and if you can use GPU machines, then you can do all of these in parallel. And that's why once the processing powers became better and you had high power GPUs, that's when neural networks became extremely popular. Now let's take a look at other algorithms which actually improve on the basic algorithm. So if you look at the basic algorithm, so far what we've looked at is in one dimension. We looked at if we have particular algorithm W1 and you have a particular loss equation, right? Then how do you update it? So you take this particular value, you take the derivative over here, you have a learning rate, and you keep on getting better and better values, and you eventually get to the optimal value of a particular in one dimension, right? Now, of course, this is not going to be limited to one dimension. If you have two inputs, x1 and x2, you're going to have two dimensions, right? So you're going to have W1 over here and W2 over here, okay? If you have three dimensions, you're going to have W3 over here. If you're going to have n inputs, you're going to have n dimensions. So you can immediately imagine how complex this is going to become. It's not going to be, as humans, we won't be able to even visualize this. Though the best that we can visualize is in two dimensions. So let's take a look at an example where we're simply talking about two dimensions, where we have W1 and W2, and you have a perceptron where you have X1 and X2, and you're trying to update W1 and W2, and you have this, again, simple example, all right? But now what we're going to try to do is try to see if we can get better algorithms, all right? Now, if you look at some of these that we've seen in the past, you remember I showed you this graph before, right? This shows you in two dimensions what a loss function could look like. This is, as you can see, the loss function is starting off over here. We saw this earlier, that it was starting off from a high point, and then this was the minimum, and it went through a gradient descent algorithm, and it found the lowest point. Of course, if you started off over here, you may end up at this particular point, and this is not very useful because you're stuck in a local minimum. So the question is, how do you get out of a local minimum? Can you do better than that? And do you have more sophisticated algorithms or not? So let's take a look at slightly more sophisticated algorithms. The first issue that exists is that let's take a look at the complexity of the algorithm. How complex is this algorithm? Okay. So if you take a look at the gradient descent algorithm, the basic gradient descent algorithm, and you take a look at the complexity, okay? So suppose that you have a whole bunch of inputs, all right? X1 se lekar ke xn tak, all right? And you have, let's say, n layers, and let's say you simply have a single output over here, all right? Now, remember that we said that the error function is not just a single function y hat minus y, but if you have a series of data points, right, then it's going to be a sum over all the possible inputs. So you're going to have a summation 1 se lekar ke s tak, and s could be, as I said, if you have 1,000 images, then you would want to train over all 1,000 of them. In the earlier example, we had 6 points, right? So you took the error over all 6. You wouldn't just take the error over one particular point, you would take the error over all 6 points, right? You would calculate y hat minus y. So for the first example, you may get a 0, you're correctly identifying a cat. In another example, it may not be correctly identifying, so you get an error of 1. In the third example, you may get 0, all right? So the error could be at times 1, it could be at times 0. So you want to take the error over all the possible samples, okay? So imagine that if you wanted to calculate the update over here for the backward backpropagation algorithm, for each iteration, what would be the complexity of this algorithm? How many steps, how many calculations would you require? So if you wanted to update, let's say W11 over here, n plus 1, how many steps would you require? And this is xn, okay? Let's assume that each one of them has n, the depth of the width of each one of these layers is n, okay? A small n, the number of hidden layers is capital N. So can somebody tell me how many calculations would be required for each one of these iterations? Go back to the equation. Go back to the equation and figure out. Certainly you would require, it would be proportional to capital N, okay? Because you remember that as the depth increases, the chain rule implies that you have more and more equations, okay? Because you're calculating the loss based on all of these samples, so certainly this would be proportional to S, all right? So for every iteration, to calculate a single loss, you need to now calculate over all the possible data sets. So if you have a data set which has 1,000 points, okay, you would have to first calculate the error over, that would require 1,000 calculations. Then you would have the depth of the neural network, and then again it would be proportional to n as well, okay? Somewhere n is going to come in as well, because you can see that the neuron over here is going to be connected to all n of these as well, okay? So you can see that the complexity of this algorithm becomes very, very big. And if you're doing this in a number of iterations, let's say you have let's say you have q iterations, right? Then you can see that this is again going to be multiplied by the number of iterations as well. So, and if each one of these is big, so for example, n could be, in large neural networks, n can be extremely big. It can be 100, it can be 1,000. So n can be 1,000. This capital N could easily be 100 in some cases. S could be, it could be 1,000,000 as well. If you have a large, if you have big data and you're trying to train on big data, and if you're trying to take a large number of iterations, you could be going to maybe 1,000 iterations. So you can see that very quickly you get numbers which are 6, 7, 8, 9, 10, 11, 12, 13, 14. You've already talking about trillions of calculations, okay? So obviously you've got to simplify things, all right? So the first thing that you want to simplify is something called a stochastic gradient descent, all right? So this is the first algorithm that we'll study. It is a slight modification of the gradient descent, and this is called stochastic gradient descent. So basically what it says is that if you have a large amount of data, okay, do we need to calculate the error over the entire data set, or can we do it over a smaller subset? Okay, as we're going through the iterations, as we're going through the earlier iterations that we saw, as we're going through these iterations, right? We go through one whole iteration, we update all of these weights, and then we apply it to another set of data, okay? So we change the data over here, and then we calculate the loss, and we update all of these weights again. So this is going around in circles, okay? We apply a new image. It could be a new image, it could be a new data point, and then we calculate all the weights again. Now, the question is, okay, when you're applying this iteration, and if you have a large number of data points over here, can we reduce this calculation? And instead of applying it to the entire data set, can we apply it to a subset of the data? And what are the pros and cons? So what do you think? Well, first of all, what is the advantage if you don't apply it to the entire data set and you calculate the error over a subset, maybe a random subset of that, okay? What do you think is going to be the advantage of doing that? Advantage would be that instead of doing it over S, right, you would immediately have a smaller set. So let's say that you do it over a batch. So instead of doing it over the entire S, you break up this into smaller batches of size B, okay? You break it up into smaller sizes of B. So each one of them is of size B, okay? So instead of doing this entire iteration over S points, you're now going to divide it over S divided by B. Because let's say if this was, S was 10 to the power 6, and each batch was 100 points, then all of a sudden, instead of using 10 to the power 6 over here, you have 10 to the power 6 divided by 100, okay? So this equation, the number of calculations becomes smaller, okay? But what do you think is going to be the impact on the error? So it would be biased, right? It wouldn't be as accurate, okay? So we're going to be able to, so if you look at the steepest this particular diagram over here, what this diagram indicates is that the gradient descent algorithm generally calculates the steepest descent, okay? What that means is, and I'll try to depict this to you, that it wouldn't go in this particular direction. And you see my arrow, right? It wouldn't go here. It would go, if you're standing on a hill, it would sort of, if you left a ball over there, you can imagine that the ball would go on the steepest descent, okay? It would naturally not go this way, even though this is descending, but it wouldn't go in this. If you let some water, for example, go down a hill, it would naturally go down the shortest path, okay? This is sort of naturally understood. How is the gradient descent algorithm doing this? The gradient descent algorithm basically is doing it by, if I take a look at this and I try to depict it in 2 dimensions now. So suppose that this is, it's in 1 dimension, it's not easy to depict what's the steepest descent because there's only one path to go, okay? But in 2 dimensions, it's a bit easier. Ajit. Okay. Let me just move this because, G. हाँ देखें ये hills आ गए आपके, right? So you can think of these as hills. There are 2 hills over here, and there are 2 valleys. These are the valleys. Can you think of this in 3 dimensions, in 2 dimensions? Is that clear? So this is like this is like a mountain. If I look at this somewhere, these are the 2 mountains, all right? And these are the valleys over here. These are the valleys, okay? So this is in 2 dimensions. Is that clear to everybody? Okay. Sorry. So this is the mountain top. Okay, loss is very high over here, all right? And loss is very high, but in between over here, there is the loss is lower, okay? But now we're going in 2 dimensions. So this is 1 dimension over here, and this is another dimension, okay? So instead of just being 1 dimension, this is 2 dimension, and we're changing both these values. And as we're changing W1 and W2, your loss is going in, in 2 dimensions, okay? So I hope this is a bit clearer, okay? So now let's take a look at in 2 dimensions. I'm going to show it as contour maps. Okay, you might have seen these contour maps where basically what we're trying to show is, let's say, okay, this is the innermost circle, and these are concentric circles. All right, and suppose the loss is the least over here. This is one of the dips, so this can be represented by something like this, but it's in 2 dimensions. All right, so this is in W1 and W2. It's a bit hard to show, but basically over here the loss is the least. This is the loss is higher over here. This is the loss is higher. Okay, so and so on. Okay, so these can be concentric circles. You might have seen this as when you're trying to show hills in 2 dimensions. You know, you might have seen this. So here the loss is very high, and let's say you start off over here. Okay, you start at a particular point, W10 and W20. Okay, so you start off these 2 points, and now the backpropagation algorithm is going to tell you that I'm going to improve this in a particular direction. And what it's going to say is I'm going to use a gradient, which is going to be, it's kind of hard to draw, but the gradient is going to be perpendicular to this particular point. So can you see that the gradient is not going to be here? The gradient is not going to go in this direction. The gradient is not going to go in this direction. It's going to be perpendicular to this particular diagram, to this particular graph over here, to this particular line. Okay, so in 2 dimensions, it's going to go in this particular point. So it's going to make a jump over here. Based on the learning rate, it's going to make a certain jump. Okay, now it's going to end up on this particular contour. Now over here, where do you think it's going to go? It's going to go in this direction, or this direction. It's going to go in the middle, because you can see that the the perpendicular line is in this particular direction. All right. Similarly, once it gets over here, it's going to, hopefully, this is not very accurate, but it's going to choose the path which is going to be hopefully the shorter, the path of steepest descent. And if you can see this particular blue line, you can see that this is most likely the path that is going to be chosen by the gradient descent algorithm, because at every point it's going to choose the path of the steepest descent. Okay, so that sort of comes built in with the gradient descent algorithm. Now, having said that, now the gradient descent is using this particular path. Why? Because it's choosing its error very accurately. It's choosing its error based on all the possible sample points. Okay, so the error is going to be, so the gradient is going to be very accurate. Now suppose that we choose a stochastic gradient descent. Okay, now the stochastic gradient descent, so this was my earlier points. All right, and let's say I was going from here and came here. So I went over this particular path, and it went to the minimum loss in the best possible way. All right. Now I'm going to choose a stochastic gradient. Now stochastic gradient is going to say I'm going to calculate the loss over here, but it's going to be on a very small subset of the data points. So do you think it's going to calculate the gradient accurately? It's not going to be as accurate as the gradient descent. So this was gradient descent, right? And this is stochastic gradient descent in blue. So the stochastic gradient descent is basically what it's doing. It is saying that I'm going to calculate the error on a subset of the data. When it's calculating it based on a subset of data, naturally the error is not going to be very accurately calculated. If the error is not going to be very accurately calculated, do you think that the whole algorithm of backpropagation is going to result in a very accurate result? It's not going to be a very accurate result. So do you think it's going to go using the steepest descent? It's not going to be using the steepest descent. So what's going to happen in practice is that it might go in the wrong direction. Okay, is going to jump to a wrong direction. It's going to jump over here. And then based on the learning rate, that will determine how far it's going to jump. Is going to again calculate based on another subset of the data. And then maybe it's going to go in a different direction. All right. And then it's going to go in a different direction. So it may eventually go to the same point, but you can see that it may not take the shortest path. It may not take the steepest descent algorithm. Okay. However, what's the advantage? The advantage is that this algorithm, the stochastic algorithm, will actually be, which one do you think is going to be faster? So this one is probably going to be faster. Why? Because even though it is, it's making mistakes, but because it's making mistakes faster, is going to get to the destination faster. Okay. And so to be able to illustrate this, there is a nice video, and let me show you that video, which explains the whole thing slightly better than my explanation. Okay. Can people online see this? And let me know if you can hear this as well, because I'm not sure sometimes the audio doesn't work too well. So people who are online, can you hear the audio that was just played?
No, sir.
No, sir.
You couldn't hear the audio? Okay, hold on a second. I think there's a way to fix that.
I still have the exact same single node.
Okay, can people hear that audio now online?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Okay. So I'm going to, this is like a 15-minute video, but I'm not going to play through the whole thing. I'm just going to share with you some clips of it. So what you see over here is a two-dimensional version with contour maps showing the same kind of scenario, except that now what you have is
Network with just the bias.
Okay, so what you can see over here, that where the contour maps are very close to each other. Okay. Okay, this is not working out. Okay, can people see this? Okay, so I hope people who are online can see my my image that I'm writing. So if you look at this contour map, the lines which are close by are indicating a steep, a steep hill. So it's sort of like this. You have a mountain over here, and you have another mountain. You have a valley over here. This portion is depicted over here. Okay, this is very steep. This, on the other hand, is very shallow. Okay, this is like you've gone into a valley, and now you're going down the valley, and it's it's a very shallow valley. It's not very sharp. It's a very gradual slope. Okay. So the point is that if you have in 2 dimensions, if you're starting off somewhere over here, let's say you're starting off over here somewhere, starting off over here, you're going to let the ball roll. And as the ball rolls, it's going to go down the steepest descent. Okay. So very quickly, it's going to end up over here. And then the gradient descent algorithm is going to force it to go in this particular direction. Okay. Now, Now, the algorithm over here is going to show you a couple of versions. There's a first version which is going to apply the stochastic gradient. Okay, the stochastic gradient is going to be a little faster. Okay, but it may not show the shortest out. So if you use the stochastic gradient algorithm, it may go a little bit like this. It may go a little bit like that, but eventually it's going to come here, and it may go sort of like this. If you can see my arrows, it's probably going to go, eventually it's going to get to this destination, but it's not going to take the shortest path, but it's going to be a lot faster. Okay. This particular actually video doesn't demonstrate the stochastic gradient versus the non-stochastic. It demonstrates another algorithm. And let's talk about that algorithm first before I can show you that. So let's come back to that. Sorry, so that particular video actually wasn't the right one to show right now. So let me talk about the algorithm that is depicted in the video. So in the video, another issue that comes in is that the stochastic gradient algorithm we've understood is going to take slightly wrong decisions, but it's going to be faster. Okay. The next issue is that can you figure out how to get through problems like this? So remember, and this is part of the homework assignment as well. Suppose you start off over here. Now, what's going to happen if you use the simple gradient descent algorithm? It's going to get stuck over here, right? Especially if the learning rate is small. So it's going to come down over here, and it's going to say, well, I found the point where the slope is 0, and it's going to get stuck over here. It's never actually going to go down over here. Okay, so there is another solution for this, and it's called the momentum algorithm. Okay. So let me write down the equation for the momentum algorithm. Momentum algorithm basically says that if you want to take Wn plus 1, you take Wn, okay? You take R minus the learning rate multiplied by the rate of change of the loss with respect to W, okay? But now what you want to do is you want to sort of be able to add something which is going to, you can think of this physically. Imagine that this is a ball, right? It's rolling down the hill. Now, if you can add momentum to that particular ball, you want it to go fast. As it's going down, you want what happens to a real ball? It starts going faster and faster, right? Eventually, when it gets to this particular point, it's got so much momentum that it doesn't stop over there. Okay, what does it do? It actually goes a little bit, it overshoots. Okay, and if this hill is not that big, it'll actually overshoot, and it'll go over here. Okay, and then again it's going to go down. It's going to go faster, faster, faster. Eventually, it's going to get to the bottom of the other hill, and then again, is it going to overshoot? Yes, it's going to certainly overshoot, and it's going to go up. Well, in this case, maybe because this is very steep, it's going to eventually go back, and it's going to overshoot again, and it's going to, eventually it's going to go back and forth, and it's going to settle down to a point which is a little bit more stable. Okay, so now the question is, how do we add momentum to this equation? All right, so this equation basically says that I'm going to take the previous value of the weight. I'm going to look at the rate of change, okay? But it doesn't really add, and it's a bit hard to actually, to be honest, be able to figure this out. So I'm just going to tell you the solution. The solution is that I'm going to add another parameter, okay? And this parameter is generally referred to as either lambda or what have you. It's good. Over here we had the learning rate. Here we're going to have the momentum constant. Okay, so this is going to be the momentum parameter, and then we're going to multiply it by the rate of change of the momentum. Sorry, the rate of change of the weight itself. Okay. Now, this may not make too much intuitive sense right now. Okay, but let's take a look at this video, which is sort of try to explain intuitively as to what's going on, and it will also help explain the stochastic gradient to some extent. Okay. That's a lambda over here. So this was an R over here. This is lambda, and this is delta W. Okay. So this is it's taking, and delta W is defined as delta Wn is defined as Wn minus Wn minus 1. Okay. So it's taking a parameter which is based on the previous rate of change of the weight. Okay, so this is, if I were to explain it intuitively, that as the ball is rolling down, okay, the weights in a particular direction become bigger and bigger. Okay, because it's all going in one direction. Once it gets to the bottom, the rate of change in this particular direction has become fairly big. So that's sort of like the momentum. Okay. Now that momentum is going to carry it forward. Okay, it's not going to make it stop. Even though this parameter is small, it's saying that the slope has become 0, it should stop. This is going to say, no, even though the slope is small, I'm also going to rely on the momentum. Okay, the momentum value is very big. So the momentum is going to say, I'm going to continue in the same direction. Okay, and then the same thing happens over here. Is going to go down this hill, and this momentum value is going to become bigger and bigger, and that's going to continue to make it overshoot. Okay, let's take a look at this video. G. So the assumption here is that this is going really high, right? एक पॉइंट यहाँ पर आकर के वो मोमेंटम कंटिन्यू किया, राइट? ओके, जब यहाँ पर आए, राइट, कम्स डाउन ओवर हियर. हाँ, तो हो सकता है उससे वाली हो. So it's not necessarily guaranteeing that it will find the optimal solution, but it's simply saying that it has two advantages. Number one, what it does is, as you go down the slope, it takes bigger and bigger steps. Okay. Why is that? Because this factor, this value becomes big. Okay, so if you're going down a particular hill, and if you're going down in the same direction, this rate of change will become bigger and bigger. Okay, so what's going to happen is that initially you might take small steps, then you're going to take larger and larger steps. Okay, that's the first advantage. The second advantage is that if you get to a local minimum, there's a probability that it's going to overshoot. Okay, there are two advantages, and it will become a little bit easier to understand if you take a look at this video. Okay, so let me just share the video. Okay, and I'll share the sound as well. So take a look at this video and see if it's making sense.
And a handful of sample points. In the previous few videos, we talked about the weight space, which you see here. I can actually zoom in, and you can see that it's actually being skewed a little bit because of the zoom. Okay, so you can see this is where I started over here at -1.
So what's being shown over here is that this is the stochastic gradient algorithm, or the gradient algorithm, and each one of those arrows over here is showing you how big a jump it's taking. Okay, so it's taking big jumps over here, but as over here it's let me show it over here. Over here, maybe I can use arrow. So you can see my arrow here, right? Good. So over here, you can see that the contour points are kind of steep, okay? But over here, they're becoming separated further and further. So as the gradient is becoming less steep, the points, the steps are becoming smaller and smaller, okay? Over here, the gradient is extremely small. So you're going to take extremely small steps, okay? And that's going to be evident in a few seconds.
For the weight and bias respectively. Gradient descent follows the steepest gradient downwards, but is also proportional to the gradient. So you see how this is very steep here, and these arrows are much, much longer than the arrows over here, which you probably can't see. Let me zoom in here.
Okay, so as you can see that the jumps are becoming smaller and smaller, and here they become so small that you can't even see them. Why is that? Because this is the standard gradient descent algorithm, which is simply saying there is no momentum, and all you're doing is you're taking the jump, which is the learning rate multiplied by the slope. Now, the slope is becoming smaller, you're going through a shallow portion, then you're going to take very small steps. And so what it's going to say is that you're going to take through the shallow portion of the hill, you're going to take very, very small steps. So it's going to take a very long time to get to the destination, okay? And
you can see they get smaller and smaller.
The momentum algorithm is going to hopefully try to overcome that. So let's take a look at
smaller and smaller and smaller. And that's because this region over here is actually shallow, is very, very shallow. Now, one of the things that would be nice would be for it to move quickly across this very shallow region right here, right? This is very, very flat. But it won't because this is strict gradient descent and the gradient isn't very large. So this is one of the things that momentum will do for us. Now let me go ahead and close this and turn on momentum like that. Okay, so now I'm plotting both. Let me blow this up. Okay, so if we zoom in here, the red arrow.
So basically what the gentleman is explaining is that, as you can see, the red arrow, the original one is the gradient descent, and the blue arrow is with momentum, okay? And you can see that the momentum actually overshoots. The arrows, the blue arrows are small initially. The red arrows are becoming smaller, but the blue arrows are becoming longer, right? Why? Because the momentum portion of that equation is becoming bigger and bigger. You're going in the same direction. The rate of change of the W is becoming bigger in that particular direction. As you come over here, you overshoot, right? Just like the ball overshoots. And then eventually you keep going forward.
Those are gradient descent. That's exactly what we.
But eventually you're going to slow down. Okay, why? Because why do you think it's actually going to change the direction? Remember, now there are two components. There is the slope, the gradient, as well as momentum. So what do you think is happening over here, right over here? The slope is becoming now the dominant factor. Okay, now the slope is forcing it to go in this particular direction, in the downward direction, going down this particular way. All right, so it's now going to
before goes directly down the slope, hangs a sharp left, and moves directly down the slope here, but very, very slowly. The blue arrows are momentum. You can see the first one is basically the same as the first red one, but now this has a little bit of speed built up, and the second one, it's a little hard to see, but the red arrow goes from here to here. The blue arrow goes from here all the way down to here. So the way momentum works is it treats the gradient as though it's a force pushing on.
Okay, so I'm not going to go through the whole thing. We'll pretty much stop over here. But basically, this explains the momentum algorithm. And as you'll see, I'll let you have the link over here. You'll see that the improvement in terms of steps, even though it's overshooting, the improvement in terms of steps is almost an order of magnitude. Instead of taking, let's say, 10,000 steps, it'll take 100, instead of 10,000, it might take 1,000 steps. So the improvement is going to be literally a factor of 10. And then he'll talk about other algorithms, which we'll talk about in the next lecture. Okay. So let me stop over here.